Max-Planck, and also collaborates in the ACT experiment, which is the topic of the talk today.
Okay. Thank you, Jose. Thanks for the invitation. I love the winter in Munich. I love the cold, the ice, but having a break, a 10-day long break, is just great coming here in the winter. Anyway, I tend to speak very fast, so please don't hesitate to stop me if you don't follow me or if you do not understand what I'm saying. So as Jose said, I'm going to talk about the results of this experiment in which I have been taking part for the last 4 or 5 years. This is the outline of my talk. I was suggested to do a big introduction because part of the audience might not be so close to cosmology and to the study of the cosmic microwave background. So out of these 4 points that you see here, the first one is going to be probably the longest one, trying to introduce in a historical fashion how the CMB was discovered and why we believe that the CMB is so important in cosmology. So I know I should not write too many equations in the transparencies in the talks, but I think these are simple and are basic. So, well, I don't know if because of observational reasons or because of reasons of searching for simplicity, but the first approach to characterize the universe was assuming that the universe was isotropic and homogeneous. On these premises, the only line element that you may write in general relativity is this one, which is known as the Feynman-Robinson-Walker metric. And out of this, you can write the Einstein equations that describe the evolution of the universe. When in the 20s, no, it was in the 1518 or so, around this, at the beginning of the last century, when Einstein wrote these equations, he found out that the universe was either collapsing or expanding. And that he didn't like, because he always thought that the universe was supposed to be static and eternal, something at rest. And for this reason, he introduced this cosmological constant, just to make the universe static. However, just a few years after he did this, in the early 20s of the last century, Edwin Hubble invited Einstein over his observatory in California to show him that actually galaxies were moving away from us, and that the farther that the galaxies were, the faster they were apparently moving, receding from us. And therefore, there was no reason for this term anymore. Einstein said that this was his biggest mistake, or one of his biggest mistakes, but actually, for other reasons, this term is back into the equations, although Einstein never got to know this. Anyway, but these equations and this discovery sets the frame for sets a frame for our understanding of the universe, in which the universe is expanding, is evolving from a very hot, small, dense phase into a larger and colder phase. This is the so-called firewall model of the universe. This was done, this was suggested in the 20s, 30s, and given this and the knowledge of physics at that time, people could think of how different components in a universe would interact to each other when the universe was younger and younger, hotter and denser. One could solve the Boltzmann equations for each of the components, like neutrino, photons, electrons, protons in the universe. There is, however, a limit in the temperature or in the density of this universe that could be characterized by the physics at that time, because at that time nuclear physics was developing, so it went through a boost during World War II, and as quantum mechanics and nuclear physics evolved and moved forward, so did the understanding of so did the application of cosmology, and in particular on the interactions of different components in the young universe. So when people understood nuclear physics, they could understand how the first nuclei were produced in the very young universe, according to this model. Right? So the picture is as follows. At the very, not an initial time, but at a very early time in the universe, you have a species of nucleons that eventually form nuclei, atomic nuclei. A bit later, the electrons recombine the nuclei to form mostly hydrogen. So all these processes were understood by the physics of those years. When the electrons recombine mostly protons to form hydrogen, then the radiation bath that was present is released and can propagate freely. This is the so-called CMB, cosmic microwave background radiation, which is supposed to have a black body. So these were the predictions for the theory. And in particular, they made predictions because they understood how nuclear physics worked. They could make predictions on the abundance of different nuclei at this very early stage. How many different nuclei were produced at the beginning of the universe, at the very early young stages of the universe. So I have stolen this plot from NetWrite's website in the internet, which shows the predictions of this Big Bang theory for the different abundances of different nuclei versus this parameter here. This parameter is telling us the energy density of the matter that we are familiarized with. The energy density of the baryons, which is just matter that interacts electromagnetically with light. Okay? So this gray stripe, vertical stripe, is telling us the observational allowed range for this common matter, right? Which is given by the vertical stripe. And the horizontal stripes tells us the measurements on the abundances, of the primordial abundances of all these species. As you see, the allowed range from omega b coincides with the allowed range for the observations for the abundances of each of these species precisely where the lines for the prediction, for the Big Bang theory prediction suggests. Okay? So there's a clearly overlap between the different stripes, the theory, and the allowed range for omega patterns. Okay? So this is regarded to be one of the main success, one of the biggest success of the Big Bang theory, predicting the amount of nuclei in the young universe, in the current universe. But as I said before, it was also predicted that there should be a radiation band flooding, throughout the whole universe, the so-called CMB. And when theorists like D.K. Peebles and Wilkinson were thinking of building a telescope in Princeton University, only 40 kilometers away, these two people working for Bell Laboratories and manipulating a new antenna found an excess, of black bodies, a noise, a source of noise that was close to a temperature of 3 Kelvin. So, this actually come to be the discovery of the cosmic microwave background. So the theory predicts that this radiation was released right after the electrons combined the protons in the very early universe, when the universe was only around 350 or 80,000 years old, at the redshift 1100. It should show a black body, and moreover, it should be very homogeneous, but it should show small anisotropies, both in the intensity and in the polarization. And these anisotropies of the cosmic microwave background of this radiation field should be tightly coupled to the anisotropies in the energy distribution of each of other components in the universe, as the theory predicted by simply evolving this Boltzmann equation for each of the species in the young universe. So, this is what the theory predicted. The theory cannot predict what is the actual CMB sky, what is the actual anisotropy pattern that we're going to measure. It just predicts the statistical properties, the average statistical properties of this field. This field is Gaussian. Therefore, it's completely characterized by its second-order momentum, either the correlation function or the angular power spectrum. What I'm plotting here, this plot, I will be showing over and over during my talk. And it's just giving the angular CMB power spectrum, which is just the average of the square of these Fourier coefficients on which we decompose the CMB sky on the sphere. If we decompose the CMB sky onto a spherical harmonic basis, we obtain these coefficients, which depend on the matter content of the universe, the baryon content of the universe, the Hubble constant, several cosmological parameters. So for a given set of cosmological parameters, the theory predicts a model for the angular power spectrum, which is giving us the amount of anisotropy in the intensity at different angular scales. This L that I'm showing here is nothing but the Fourier mode of the angle on the sphere. So large values of L correspond to small angular scales. Low values of L correspond to large angular scales, to big angular scales. So the theory predicts the solid line. The theory, given a set of cosmological parameters, the theory predicts how much anisotropy will have at different angular scales. Okay. But actually, we can only see one universe, which corresponds to one single realization of this random form. And this is shown here by these diamonds. For this map, you get this level of anisotropy at different angular scales. So we have very different patches where we can sample the small scale modes, the high L small scale modes. And therefore, the dispersion around the theory model is small on the smaller scales. But on the very large scales, we have just a few independent modes, and therefore we have a bigger scale, which is called cosmic mode. The theory simply predicts this, and cannot predict, how much scatter we have, what is the actual position of these diamonds in the real sky that we measure. But at least, the theory can characterize the average statistical properties of this Gaussian. So this is our understanding of the universe. From the Big Bang, initial moment of Big Bang, we have nucleosynthesis. we have the formation of the first atom. We have recombination, electrons recombine protons to form hydrogen. The CMB is released then in this epoch and starts traveling throughout the history of the universe until it reaches us. So there is some period where there is no stars, which is called the Dark Ages. Then the first stars arise and ionize the universe. First galaxies form, first galaxy clusters form, and then we seem to have some evidence for an accelerating universe. That is, we seem to have some evidence that the universe is expanding in an accelerated way, which is a very late epoch, so very low redshift, below redshift 1 or something. So this is what the model is. That, this is how we believe the universe is working right now. So in 1992, the mission COVID, the satellite COVID, measured by first time the spectrum of this CMB, cosmic microwave background radiation, and he found the most perfect black body that has been measured today. He not only measured the total spectrum, but he also measured anisotropies. Anisotropies on the largest scales, because its angular resolution was rather poor, was around 7 degrees. This, however, was compatible for being with the theory, and the theory was further confirmed with a subsequent, with many other experiments, but in particular with WMAP. WMAP, I'm showing here the results from the year 2010. WMAP has a finer angular resolution. So it goes from 7 degrees from COVID times down to 0.2 degrees. So we see the smallest scales. Sure? And we see here how they predict, how the measurements, which are given here by the black dots, are following the theory predictions very neatly. Both in the angular power spectrum of the temperature, of the intensity of the CMB, and also WMAP has measured the polarization of this radiation, and the polarization is predicted by the theory to be correlated to the intensity. And this correlation between polarization and intensity is given here. Right? And still follows theory very neatly, very accurately. So, what is the meaning of this plot? I don't want to get deep into the physics of the CMB, but essentially showing us that at the epoch of the coupling, at redshift 1100, when electrons recombine protons and the radiation is released, the universe subtends a typical angle of 1 degree. So all spots that are smaller than a 1 degree size, in this map, are corresponding to sub-horizon scales, are connected causally. Whereas all spots that are bigger than 1 degree are corresponding to supra-horizon scales at the moment. Right? So this is something here like this. Okay? I get it. Okay. Yeah. So this is sub-horizon scales, and this is telling us that these acoustic peaks that you see here essentially reflect the fact that at that redshift, the photons and the electrons are coupled by thomson scattering, and they are oscillating in the potential wells. So they have fundamental modes of oscillation, which are given by these acoustic peaks. And then on larger scales, beyond the horizon at that high redshift, what you just see is a plateau here, which is caused by the large-scale supra-horizon fluctuations in the gravitational potential. So we see fluctuations coming from two distinct patches of the sky that were never causally connected, but which were sitting on different potential wells of different amplitude. And this is the level of anisotropy that we are finding at L below 200. So the theory is so far confirmed, but there are still many tests to be made, like going to smaller scale. So after WMAP, other experiments went to higher and higher L, that is to smaller and smaller angular scales, going up to L equal 2,000 or 3,000, but there was some kind of vacuum, not really trustful results in the very small scales. And actually there is a lot of physics intervening here in these very small scales. So the acoustic pattern that I was talking about a minute ago is suppressed at the smaller and smaller scales. Yes, because the oscillation of the photon barium fluid is not perfect, because since the coupling is not perfect, the photons can typically travel from some distance before they encounter the new electron. So this typical diffusion length is actually suppressing the anisotropies on the very small scales, which are comparable to the photon mean free path at the coupling, at that high redshift. And then we have other secondary effects that are going to come up here, as I will show now. So this is the motivation. Probing this scale range in the CMB is the motivation for experiments like the Atacama Cosmology Telescope. So what is the Atacama Cosmology Telescope? So let me play the politics. It's a big collaboration. You have here the member list from many institutions all throughout the world. It's led by Princeton University, but there are collaborations in Chile, in Canada, and in Europe. And well, what is it? It's this telescope that is shielded here. So there's a telescope here of 6 meters diameter, which is shielded from the ground radiation by this curtain, iron curtain. And then, well, it's a very high place. It's in Cerro Toco, in the Atacama Desert in Chile, and it's the highest telescope today, I believe, right? In a very extremely dry place where the skies and the atmosphere is very stable. It has very high angular resolution, 1 minute, which allows us probing the high yield, the small scale fluctuations of the CMB. And it's measuring at 3 different frequencies, which are of particular interest for CMB studies, for cosmic microwave background studies. So this slide compares experiments in the last few years in a schematic way. So COBE was measuring large angle fluctuations in the CMB. Next step was WMAP, which was down to 0.3 degrees. Planck, which is currently scanning the sky, is improving things slightly, but with many more frequencies. Finally, ACT is giving a step beyond, and is really probing the very small scales in the CMB, where new sources that we'll talk about in what follows are entering and are becoming important. So this is the range, the multiple range, or the angular range where ACT is going to be sensitive to. We will see the silk damping, the damping of the initial anisotropies, which are being lensed because there is matter in the way. Well, as I will explain later, these fluctuations are being lensed by the intervening matter along the line of sight. And then you have other secondary effects that we'll talk about now. Secondary effects are arising as the CMB travels from the last scattering surface towards Earth, because there are a number of different episodes during cosmological history that are changing the pattern of the anisotropies of the CMB. For instance, here I'm showing first schematically the linear anisotropies. That is the anisotropies, the secondary anisotropies introduced in the largest scales. This is the intrinsic CMB power spectrum that is released at recombination at redshift of 1100. But when the first stars reionize the medium, there are new free electrons along the way of the CMB photons that interact with the CMB photons, and they slightly blur the original isotopies. Here the thin line shows the original isotopies. Because of this new scattering, they are slightly blurred, they are slightly erased. So this is a negative term. This red is in reality negative, and it's suppressing a little bit the smaller scale power. And this new scattering is introducing some further anisotropy. This point here is positive on the very largest scales. Much later, when the universe starts to expand in an accelerated way, there should be a new set of anisotropies introduced on very large angular scales. And this is due to the fact that if the universe is expanding in an accelerated way, the large-scale gravitational potential walls are not constant, but are shrinking. They are becoming shallower. So photons closing them are going to gain some energy. And this introduces some new kick, some new level of anisotropy. This is called the integrated Ashworth effect. These are anisotropies that are being introduced in moderately large scales. But this is not the whole thing of the story. This is not the whole story, because on the smaller scales, there are also secondary anisotropies. So this is a simulation. Anyway, in this simulation, I'm showing secondary anisotropies that we expect to arise at very small angular scales. These scales are corresponding to a few arcmins. So maybe I should have said this before. L of 200 corresponds to 1 degree, and these are few arcmins. So as the universe evolves, there is a population of radio sources, of dusty infrared sources that are forming stars at moderate and high redshift, and their fluctuating number along the line of sight are introducing some further anisotropies on the CMB. These are secondary anisotropies, and they are showing up in the small scale range. There is also another secondary effect of great importance in terms of cosmology, which is called the Sunyaev-Zel'dovich effect, that we'll talk about now, which is given by this red line. So this is the type of secondary anisotropies that ACT should be sensitive to, and that we target in our observations. What is the Sunyaev-Zel'dovich effect? The Sunyaev-Zel'dovich effect simply describes the interaction of CMB photons with electrons, with a cloud of electrons, which is depicted here somehow. So the way of interaction is just Compton scattering, but you have two regimes of Compton scattering. If there is no energy transfer, If there is no energy transfer, then essentially in the scattering, the CMB photon doesn't change frequency. Just changes direction, but does not change frequency. But if the whole cloud of electrons are moving with respect to the CMB, then all photons of the CMB are getting a kick, are being kicked by the cloud of electrons, and there is some Doppler effect, which is given by this term. This term is called the kinetic Sunyaev-Zel'dovich, and it affects equally all photons of the CMB. So, since the CMB has a thermal spectrum, a black body spectrum, this channel of interaction, this effect, does not modify this black body spectrum because it affects equally all photons of all frequencies. Okay? And this is non-zero, and this is sensitive to the peculiar motion of the cloud of electrons. At the same time, if these electrons are hot, like 10 to the 8 Kelvin, then in the scattering, there is some energy transfer, and this is called the thermal Sunyaev-Zel'dovich. In this case, you have a cold photon that when it encounters some hot electron, then it gains energy and becomes more energy. In this case, the way that energy is transferred from the electron gas to the photon gas depends on the frequency. And therefore, in this case, you really change. Your effect is not democratic among photons because you are being more efficient with low energy photons as compared to high energy photons. And therefore, you are distorting the CMB black body spectrum. And therefore, these anisotropies in temperature are depending on frequency. In a black body, the brightness temperature does not depend on frequency. And therefore, these anisotropies here, since they do not modify the black body spectrum, do not depend on temperature. But these ones, because this scattering is not democratic, and is affecting some frequencies more than others, then this does change the spectrum and thus introduce frequency-dependent temperature anisotropies. Okay? So why is this so relevant? This is relevant because there are not many ways to find a cloud of electrons in space. A cloud of electrons in space, if the gas is ionized, and we believe that most of the matter in the universe, in the low redshift universe, is ionized, we cannot simply see it because they don't form stars, they don't form molecules, they don't have lines. There is not an easy way to see these electrons floating in space. And two possible channels are these two effects, and both use the cosmic microwave background. Okay. Actually, this cloud of electrons are found in some structures that are associated with galaxy clusters. So galaxy clusters. Galaxy clusters are the largest bound structures that have formed in the universe. And in particular, they have their baryonic content is mostly dominated. It's dominated by a plasma, by a cloud of hot electrons, where both of these effects are taking place. So in this sense, the cosmic microwave background can be used, the Sunyaev-Zel'dovich effects can be used as a tool to probe and to sample and to measure the population of galaxy clusters at different cosmological epochs. Let me elaborate this point a little bit. So the thermal Sunyaev-Zel'dovich effect, the one that depends on frequency and on temperature, does not depend on it. Its surface brightness does not depend on it. So here you see the detection of the thermal Sunyaev-Zel'dovich effect in three different galaxy clusters placed at very different redshifts. And here you can see the corresponding X-ray images. While the X-ray images, its flux is going down, is decreasing with redshift very rapidly. You see that the thermal SC effect does not appreciably change over time. Therefore, this thermal SC effect, this thermal Sunyaev-Zel'dovich effect is a very powerful tool to probe clusters at high redshift and to probe baryons in an ionized state. Is this relevant? Well, this is relevant indeed, because as I said, galaxy clusters are the largest bound structures that have formed in the universe. And the abundance of these structures versus redshift is very much dependent on the type of universe that we have. If our universe is accelerating very much in the last epoch, then the collapse and the generation of these bigger structures, of galaxy clusters, is suppressed. And therefore, the number density should decrease. Otherwise, if indeed the acceleration doesn't take place, then more clusters are being formed, and therefore we would expect to have more galaxy clusters at very high redshift. Therefore, one can put constraints on dark energy by looking at the abundance of galaxy clusters. What is dark energy? Dark energy is just supposed to be the component of the universe that is causing the universe to expand in an accelerated way. We know nothing about it, or very little about it, and actually the abundance of galaxy clusters at very high redshift that can be detected through the thermal Sunyaev-Zel'dovich effect can set strong constraints on the nature of this dark energy component. Also, the kinematic Sunyaev-Zel'dovich effect, which is sensitive to the peculiar velocity of the universe, may help us to find the missing baryons. As I think I said before, at least half of the baryons in the low redshift universe, have not been detected. We don't know where they are. Simulations, hydrodynamical simulations, are telling us that these missing baryons should be in a diffuse state in the intergalactic medium at a temperature of between 10 to the 5, 10 to the 7, and therefore they are hard to detect. But these missing baryons should leave a signature on the CMB by means of the kinetic Sunyaev-Zel'dovich effect. So in this sense, the CMB may be a useful tool to probe, to pin down the nature of dark energy and to search for the missing baryons. So this is the kind of things that we hope to do with the Atacama Cosmology Telescope. And, and this is the angular range. Therefore, there is a wealth of new physics arising at this small scale range of the cosmic microwave. I forgot to mention that, so there is the population of galaxies that an experiment measuring in these frequencies is going to find are essentially two, either radio sources, which are essentially star-forming galaxies, or AGNs at moderately and high redshift, and dusty galaxies, that is galaxies that are emitting in the infrared because they are forming a lot of stars. They have a lot of dust that is reprocessing the UV radiation from the stars into the millimeter and into the infrared. So these are the two populations of galaxies that we expect to measure at these frequencies and find. And of course, the Sunyaev-Zel'dovich effect that I was talking about yesterday. So do we see this in our data or not? That was the goal for these observations. Here I'm showing the scale coverage for the ARC surveys so far. So we started scanning this stripe, this southern stripe, which is centered at minus 53 degrees in declination. It has a width of around 5 degrees. You see that we chose this stripe because there were two optical surveys at this declination. Made with the South Africa Telescope Planck. This is the BCS survey at 5 hours and 23 hours. Right? We also cover the so-called stripe 82 from Sloan. This is one of the few southern stripes that Sloan has covered. Particularly, this stripe is very deep. It's deeper than the rest of the Sloan survey. So you see that this year, in 2008, we have covered this stripe along with other regions. Okay. So this is so far, I think we have covered at the moment 1,200, like 1,200 square degrees, and we plan to cover like up to 3,000 in the next few years. I have the exact numbers later on. But this is so far the strategy and the sky that we have covered. And this maps. So for this analysis, I'll be showing only the data corresponding to 148 gigahertz. And we will focus on the cleanest region of this stripe, which is farther from the galaxy, from the emission of the galaxy. And this is what I'm showing here. This is the stripe. This is the central declination. This is right extension. And this is the sum map, and this is the difference map. You see that we are lucky to see more structure in the top panel than in the bottom one. This means that we have something. This map is showing the sensitivity, which is defined by the time and the scanning strategy, the observation time and the scanning strategy of the experiment. Because of the scanning strategy of the experiment, you see this kind of X pattern in the sensitivity map. So let's look at these maps in more detail. So this stripe was divided into 13 patches of 4 by 4 degrees each. And one of those patches looks like this. Oops. What you see here is that, first of all, you see some big spots. These are the small-scale CMB intrinsic fluctuations coming from the scattering of, coming from the surface of laser scattering, coming from redshift 1100. But you also see small circles here and there. These circles, these blocks here, are not in the CMB, but are point sources in this case. And you see here, you also see a cold, fine point source. This cold spot is actually a thermal Sunyaev-Zel'dovich cluster. Why is it cold? It is cold because at 148 gigahertz, the thermal Sunyaev-Zel'dovich effect is absorbing photons. So actually clusters appear as negative sources rather than positive ones. And this is great, because at this frequency, clusters can be more easily distinguished from point sources, just because they absorb photons. Okay? This behavior changes for the other frequencies. ACT is measuring not only at 148, but also at 220 and 280 gigahertz. And this pattern, so at 220, this pattern for the thermal Sunyaev-Zel'dovich effect should be 0, and should become positive at 280. So the choice of these frequencies obeys to the need of identifying clusters from the other point sources. Okay? So we wanted to confront, the first thing that we try to do with this data is to compare this with theoretical expectation, with our understanding of the CMB. And therefore, we computed the angular power spectrum of the 13 patches. We computed the mean power spectrum, and we computed the dispersion with respect to the mean, and use this as an estimate from our errors on our power spectrum. So what did we obtain? Obtain this. So this is the 2D power spectrum. This is the horizontal K mode, and this is the vertical K mode. This corresponds to right ascension, this corresponds to declination. You see? So there is a stripe to which we are not sensitive, because the experiment is scanning at constant elevation in azimuth. We cover to the same field when it's rising up on the east, and then we go back, and when it's setting on the west, we cover it again. Therefore, we have cross-linking. We have the same field covered with different angles, and this allows us to solve for systematics and for the K emission and so on. But this scattering strategy is preventing us from using this thin stripe at the horizontal frequency. Okay, and as you see, this is the 2D thing, and up to L2000, we see that the intrinsic CMB is dominating. This is this bright red ring at low L. Low meaning below 2000 or something. Right? And then we see that we follow perfectly, we follow very well the theoretical prediction from the model. And then we find some excess kicking in, at L around 3000 and beyond. This excess is incompatible with the CMB. We did try calibrating our maps with Uranus, with the planet Uranus, but we also cross-correlated our maps from ACT with existing WMAP maps, which are sensitive to bigger angular scales, that is, to lower multiples out. And we see that the cross-correlation, again, falls very well over the theoretical model. Okay. So this is our power spectrum. That compares pretty well with our competitors. So the South Pole telescope is a huge telescope, 10-meter telescope scanning the CMB sky, frequency is similar to ours, with a similar angular resolution in the South Pole. And this is the power spectrum that they came up with. And this is ours. So they're pretty compatible. Okay. So what is this excess due to? Well, with one single channel, right now we're just analyzing this power spectrum that we measure at 148 gigahertz. With one single frequency, it's not easy to distinguish the radio source population from the infrared source population. And actually, we find out that this excess is compatible with a single population of not clustered, unclustered, quasi-distributed sources, which is given by this brown line. There is no effect, there is no hint, no evidence, however, of any impact of the Sunyaev-Zel'dovich effect at this frequency, at least in the power spectrum. That is, the whole excess could be caused by a single unclustered population of sources. We still do not know whether infrared or radio, but they seem to be unclustered, and this explains the whole excess. And we see no evidence. This is a theoretical prediction for the Sunyaev-Zel'dovich effect, for the impact of the thermal Sunyaev-Zel'dovich effect of clusters on the CMB. And we apparently see no evidence of it. Okay? But the fact that we don't see evidence for this imposes some constraint on sigma. Sigma is just telling us the amplitude is related to the initial amplitude of the initial fluctuations of density perturbations in the universe. The fact that we don't have too many clusters, the fact that we don't see clusters in the angular power spectrum is telling us that the initial amplitude of the fluctuations that later gave rise to the galaxy clusters is smaller than this given number, 0.85. Okay? But the fact that we don't see galaxy clusters here does not mean that we don't see galaxy clusters in the maps. So here I'm showing a couple of examples. Right? This is a neat example. This is the so-called Barrett cluster. The Barrett cluster is a merging system. It's a huge galaxy cluster that is known to have undergone a recent merger. So you have two subhalos which just cross each other. But however, the dark matter has, because it's collisionless, just crossed each other, and you see actually two different knots, two different centers for the dark matter distribution that I'm trying to point out here. These contours of the dark matter have been reconstructed using lensing observations. But however, if you look at the gas emission, if you look at the X-ray emission, then you see that because gases collide, there is a subwave in the middle between the two knots of dark matter, and this is causing the X-ray emission, which is the profile that you see here, which is actually given by the black contours. The thermal Sunyaev-Zel'dovich effect is caused by the electrons, by the gas, and it's also tracing the X-ray contours. Okay. So this is one example. Another example is this one. This big cluster is now to be made out of two components, but this one is to be much thinner and contain less gas than this other one. So for arc sensitivity, in this row of observations, we just observe the most massive one. Not the left, but not the second one. Another cool example is this one. The good thing about the strategy, the scan strategy that has been adopted, is that we have scanned a region, a stripe here, that has already a lot of optical data, because Sloan did for us all the optical work. So whenever we have a detection in the millimeter range, whenever ACT finds a cluster or a strange source, we can go straight to the optical catalog of Sloan and try to find out where it is. One of the clearest examples is this one. This is one of the highest significance detections for a cluster in this stripe, in the stripe 82 from Sloan. A huge decrement here. And then, in a minute, we went straight to the Sloan data and identify a cluster, a very big cluster, and at a redshift as high as 0.82, 0.81. We're finding clusters. Half of them were known, half of them are new. There's still a lot of work in progress, but this is really looking neat. Like future, we plan to cover. First of all, we have to analyze the existing maps at 220 gigahertz and 280 gigahertz, which is going to help us a lot to distinguish between the infrared and the radio populations. But also, we're going to cover up to 4,000 strings density and in polarization as well. Right? And we have to extract a lot of physics. We have to extract a lot of physics because of the lensing of the CMB signal. Actually, I never explained this properly, but I know how far this plot is. Maybe here. But anyway, I just wanted to explain that the fact that this is the initial pattern for the CMB scales, but because there is matter in the line of sight from the surface of last scattering from redshift 1100 up to now, the factor of lensing, the mass distribution is actually lensing, is deflecting the light rays of the CMB photons, and is smoothing the pattern, right? And this, and this smoothing can be detected with ACT observations, and we have to do it with the current data that we have. Okay. And there's a lot of, we can study the gas in clusters. We can put constraints on dark energy according to cluster abundances. We can check for emission variance. There is a lot of work ongoing right now. And we hope to address successfully most of these points in the coming months and years. I don't know if I was too fast, but
Okay. Thank you very much. I think it has been a very interesting talk. Yep.
With all the three frequencies, could you estimate the redshift of the clusters?
No.
No.
No. The redshift, the thermal Sunyaev-Zel'dovich effect, as I said, is redshift independent.
Okay.
So you need optical observations for that.
Thank you.
More questions?
Carlos, could you comment on the potential of the ACT to constrain dark energy? I mean, what do you think will be the constraint that at the end of the experiment could be put on the parameter of the equation of state? What percentage confidence level?
I think this depends on two things critically. One is the value of sigma 8. How many clusters we actually find. Sigma 8 is defining the amount of clusters that we're going to detect, the 100. The other one is to what extent the quality of the maps at 220 and at 280, right? So we're working on that. We managed to understand properly 220 and 280. I think we can do a good job in that sense. How good? It's hard to tell. My guess is maybe 5% in the equation of the state or something like that. But for that we have to understand very well point sources in clusters too. We have to. It's like the game is being played in different fronts at the same time. In order to be sure about the cluster abundance, we have to understand the point source population, because some point sources might be veiling the presence of some galaxy clusters and so on. So yeah, it's hard to give a number for the precision on the dark energy parameter at this moment. I think we need more time. I mean, we are finding clusters. We're finding a lot of clusters, and this looks promising. But quoting now a precision might be a bit too premature. I wouldn't dare to say anything. Maybe I said 5%, but maybe I shouldn't have. I withdraw that figure. It's roughly in the ballpark that we expect. Around 5%. We'll see.
More questions? What is the limit of the mass of the cluster that you can find at a high redshift? So it's
the mass limit on
the mass limit. So because you can reach, for example, if you go nearby, you can detect, for example, groups of galaxies. Or
so nominally, the limit was 2 times 10 to the 14 solar mass, right? For a single cluster, for a single detection, nominally. But that was without, that is hoping, and I think that's a fair assumption, that we can remove point source contribution decently. But then we can do stacking, and in that case, we can lower the threshold and hopefully detect groups. I think my personal opinion is that we will detect groups pretty well. I mean, even Planck could do it, so this experiment is far better. So I think, I'm pretty confident that we can do well. So.
One question related to that one. What is the distribution in redshift of the cluster that you expect to detect?
So
what is peaking? Redshift 0.5, 1?
0.4, 0.5. It has a white tail at 2.6. But it's peaking around 0.4, 0.5. Yeah.
And extending up to
1 point something, 1.1, 1.2.
So, Carlos, when you put the graph with the excess at high L, so you predict the contribution from sources, and then you set an upper limit to sigma 8 from the Sunyaev-Zel'dovich effect that you
for the constraint on the Sunyaev.
But I don't understand how can you disentangle between both contribution with only having one frequency. So
that's
you
why
can
we
also
don't.
Sorry?
That's why we don't. We see that the excess we see here could be perfectly caused by just one single unclustered population of sources. So we don't have no requirement for a second. Had we obtained some excess here, then this term should be higher up. Because we know what the shape for an unclustered source population is. This is the shape. This is assuming that sources are not correlated, are just Poisson distributed. So this is easy, right? Then we see no need to have an extra component here. All the excess can be explained by a Poisson component, right? And this means that, okay, then this extra correlation term, this different shape out to the Sunyaev-Zel'dovich effect must be lower than some numbers so that we don't see it on the data. So actually we just identify one single component. We hope, when we go to 2, then the radius would go, the infrared should go up. The thing is that the infrared, this is a simulation, this is the radium which dominates, this is the Sunyaev-Zel'dovich in the red color. and the green one, which are the infrared, are clustered. So they have a shape similar to the radio on the very high L, but at lower L they are clustered and they have a different shape. So by combining 145 to 220, we hope to disentangle this component.
More questions?
I'm just curious. How do you operate a telescope at 5,000 meters?
Well, it's I've never been there, I must say. I've never been. I wish I had, but I know that they have, in the working room, that you have an office there. You saw the building, the offices close to it. They have special oxygen tanks there for the people working there. People are not allowed to stay overnight. They cannot stay overnight. And, the presence of people there is minimal. So the base is in San Pedro de Atacama, which is like 1 hour drive. Some people drive every day and go back. But yeah, that's so for some time, people who built the pipeline had to work there in place. They can tell you funny stories. But actually, building.
But now it's operated automatically.
No. There's people going there. There's people
Every
going
day. So
I'm not sure about this, but almost every day. Yeah, pretty common. Yeah. They go drive back and forth. Almost every day. Yeah.
You didn't yet show us any polarization measurements. Can you comment?
No, we have not yet. We haven't done any polarization. We will do soon, like next year or something. But right now we are not sensitive to polarization.
Thanks.
More questions? Okay. If there are no more questions, then let us thank our speaker again.